Hello everyone, welcome to lecture 29 of this NPTEL course on Riemannian geometry. So in the previous lecture I stated the local Gauss-Bonnet theorem, and then from that we proved the global Gauss-Bonnet theorem, which gave us a beautiful relationship between geometry on one side in terms of the total Gauss curvature, and then topology on the other side in terms of the Euler characteristic. So in this lecture and the next one we will proceed to prove the local Gauss-Bonnet theorem, which if you remember was basically just a generalization of the sum angle property of triangles, right. So the key technical tool is the so called rotation angle theorem of Hopf. So that is what I will prove in this lecture, and in the next lecture I will use that to complete the proof of the local Gauss-Bonnet. Okay, so let me start with a proposition. So let gamma be a simple regular smooth curve in R2. So I am first going to state and prove the rotation angle theorem just in the plane, and then we'll move on to more general curved surfaces. So let gamma be a simple regular smooth curve in R2 with unit speed. Okay. Then there exists a smooth theta such that the velocity vector is simply given by cosine of theta t del by del x plus sine theta of t del by del y. So we know that the velocity vector will give you some vector on the circle because the speed is 1, but we want to claim that in fact we can parameterize that point on the sphere by this angle theta. Okay, moreover theta is unique if we specify an initial condition. So if we specify that theta a is an angle between minus pi to pi, right, because otherwise you could just add 2 pi or integral multiples of 2 pi to theta and you would still have a valid angle parameterizing the velocity vector. So we normalize so that theta of a is in this interval minus pi to pi, so then that sort of fixes a unique angle theta. Okay, so the proof uses covering space theory. So if you haven't taken a basic course in topology on covering spaces and fundamental groups, you can skip this proof and just take the proposition on faith, right. But if you have seen a bit of covering spaces, then this is a very nice application. So the idea is the following. We have, if you look at the velocity vector, that is a function from a to b to the circle, right. Now the circle has as its universal cover r, and this map pi is simply given by cos t and sin t. Okay, that is a covering map. Then by this is a basic fact we learn in the theory of covering spaces, is that if you have a curve such as this, because r is its universal cover, r is simply connected, there exists a unique lift as long as you specify the initial value, right. So there exists a unique theta, so I am going to call the lift theta. So there exists a unique theta such that I specify the value of theta at some initial point, let us say a, and such that this diagram commutes. So this diagram commutes. which means that that gamma dot of t is basically pi composed with theta of t, but pi composed with theta of t is precisely cos theta of t sin theta of t. Okay. So that is what I had claimed in the proposition. As I said, if you haven't seen the theory of covering spaces, just take this at faith that this proposition is correct. Okay, and moreover, when you are working with smooth manifolds, the theory of covering spaces also tells you that these lifts are in fact smooth. So theta would be a smooth function. Alright, so now suppose gamma is only piecewise smooth. Okay. So with our notation from the previous lecture, suppose we have a partition A0, A1 etc. up to Am such that gamma restricted to Ak minus 1 to Ak is smooth. Okay. Then we can extend, so let us say gamma is a curve like this, right. So as long as let us say this is our A, gamma of A which is equal to gamma of B, let us say it's a closed sorry it actually does not have to be closed. So let us say you have a curve like this, and let us say this is gamma of A. Okay. So now what I do is I start with gamma of A, I traverse all the way to the first non-smooth point, I have my definition of theta from the proposition. At this I basically introduce a jump in my theta, and the jump is precisely given by the external angle. Okay. So so for t from A to A1 we have a theta from the previous part from the proposition, then we define theta of A1. So this is a definition to be the limit as t approaches A1 from the left of theta of t, but then you want to add in the exterior or the external angle at this point. Okay, and then you take this as the new initial condition, apply the proposition, have a theta that works all the way up to the next non-smooth point and so on. So you keep doing this, right. So in general we basically, having constructed theta on this interval A to Ak, we define theta of Ak to be simply the limit as t approaches Ak minus of theta of t plus the kth external angle. Okay, so in this way we get a theta which is defined on all of AB such that theta restricted to the open interval is smooth and theta is only continuous at Ak from the left, sorry, from the right. Okay. And the main point is that for all t not equal to Ak, we have that gamma dot of t is given precisely by cos theta t del by del x plus sin theta t del by del y. Okay. All right. So then the main sort of rotation angle theorem due to Hopf, so this is due to Hopf, says the following remarkable fact, that let gamma be a piecewise smooth simple closed curve with the speed at the smooth points normalized to be 1, then we get this angle theta from above. So the remarkable fact is that theta b minus theta a is precisely 2 pi. So essentially you are as you traverse along, so let me draw a picture. As you traverse along a closed path, your velocity vector makes exactly a rotation of 2 pi degrees. Okay. So if you plot the velocity vector, it basically makes exactly one rotation. Of course the velocity vector might sort of increase and then might again decrease and so on. The angle that it makes with the x axis might increase, might decrease sometimes, etc. So it is not monotonically increasing, but eventually when you come back to your origin point, your velocity vector has made a total rotation of 2 pi. Okay. So this is quite a remarkable theorem. So let's prove this. So the first step is to try to prove this for smooth curves. So assume that gamma is smooth. Okay. And so without loss of generality, by potentially rotating my picture and translating, all of these are isometries of R2. So that should not change anything in the theorem. So without loss of generality, I can assume that gamma A is equal to gamma B is equal to the origin, and gamma dot of A is equal to gamma dot of B. It is smooth, so there is no sort of corner, so these velocities agree, and I can arrange so that this unit vector is precisely the standard vector in the x direction. So let me draw a little picture here. So something like this, right. So at this point the velocity vector points in the x direction. So now in order to prove this theorem, I also want to look at the angles that various secants make. So I do not only want to look at the tangent vectors, I also want to look at the secant vectors. So for this I do the following. So I consider the following triangle. So here is A B, here is A, here is B. Okay, so for T1 less than equal to T2, so this is basically I mean if you plot the points T1 and T2, you basically get this triangle that I have drawn. So for these points I want to so let us say this is gamma of T1 and this is gamma of T2. So I want to look at the secant line whose tail lies at gamma of T1 and head lies at gamma of T2, and I want to look at the angle it makes with the x axis, right. So I want to call that phi of T1 T2. Okay, so the question is, how do I define phi rigorously, right. So this is similar to our theta. Our theta was basically the angle that the tangent vector makes with the x axis, but then we had to use this sort of covering space theory to formally define this angle theta. So I am going to do something similar with phi. Okay. Alright. So, so also I should mention that for convenience, actually maybe I do not need that so far. Okay. So, so to define phi, so the main goal now is to define phi. Okay, so we consider the following function. So v of t1 t2, this is basically going to be the unit vector in the direction of this secant line that I have drawn, of the secant line, right. So it is going to be gamma of t2 minus gamma of t1 divided by the norm of this, okay, where t1 is strictly less than t2 and right, and t1 is not equal to a and t2 is not equal to b. Okay. If t1 is equal to t2, I just define it to be the velocity vector at that point. Okay. And then I also want to look at the boundary points. So suppose t1 comma t2 is a comma b, then I want to define this as minus gamma dot, because the idea is that if you are approaching from here, so t2 is approaching b and you are approaching from here, the angle would basically point in I mean will essentially be the velocity vector at a but pointing in the opposite direction. Okay, and similarly I want to define it to be gamma dot of a if t1 and t2 is equal to a. Okay. So then one can check, this is not particularly difficult, but it is a good exercise, so I will leave that to you. One can check that v is in fact a continuous function from the triangle to S1, this is continuous. Okay. Alright, so now note that we are again in this situation where we have a function v from a triangle which is also simply connected to S1, and then we again have this universal cover, right. So again by the theory of universal covers, there is a lift of this map. So there exists a unique phi such that we specify the value at a comma a, let us say. So if you go back, what is v of a comma a? By our by rotation and translation of our picture, we are assuming that v of a comma a is del by del x. So any secant angle, so what is the goal? The goal is to define the secant angle. Any secant angle would then basically I mean this ought to be, so this ought to be cos of phi a comma a and sin of phi a comma a del by del y, right. So that means a suitable normalization for phi is we put phi of a comma a is 0, and secondly we also of course want this to be a lift, which means that v is equal to cos of phi sin of phi, okay, because the universal cover map, remember, is t going to cos t and sin t. Okay. Alright, so now we just try to trace the values of phi. So here are some observations. So firstly, if you take theta b minus theta a, okay, so that is obviously going to be phi of b comma b minus phi of a comma a, which is phi of b comma b. So in order to calculate the difference between theta b and theta a, it is enough to actually calculate phi of b comma b. Okay. The second point is, let us look at the values of phi of a comma t2. So if you go back to our picture, if you take any gamma T2, phi of a comma T2 is basically the angle that the secant line from gamma of a to gamma of T2 makes with the x axis. Now because I have normalized so that the picture is tangential to the x axis at a and the entire picture is above the is in the upper half space, clearly phi of I mean this angle with the normalization that phi of a comma a is 0, this angle is going to be between 0 and pi, right. You take whichever point you want, this angle is going to be between 0 and pi, okay. So this angle is going to be between 0 and pi, alright. So then by continuity implies that phi of a comma b, so this is for all T2 in a to b, okay. So then phi of a comma b, remember that I mean v of a comma b is minus gamma dot. So then clearly the only choice available for phi, if it has to satisfy this relation, because remember v of sort of a comma b is minus 1 comma 0, this vector. So the only choice for phi is that it has to be pi, right. Okay. Now we look at phi of T1 comma b. So if you go back to the picture, we are now looking at the top of this triangle, okay, where you are looking at a point whose second coordinate is b, and we know that here your phi is equal to pi, okay. So now if you take some T1 here, gamma of T1, you are measuring the angle from gamma of T1 to gamma of b. So clearly that angle is going to the angle it makes with the x axis is clearly going to be between pi and 2 pi, okay. So clearly this angle is going to be between pi and 2 pi. So again by continuity this implies that as you let T1 approach a, T1 approach b, phi of b comma b is going to be 2 pi, but by the first observation this implies that theta b minus theta a is 2 pi, and we are done, okay. So this completes the proof of the rotation angle theorem for smooth curves. Let us now talk a little bit about non-smooth curves. Here I will just indicate how the proof goes. For the details I will refer you to Lee's book, but suppose gamma has actually vertices. So let us focus on one such vertex and I will tell you how to modify this argument, or rather how to reduce to the first case. So the idea is we smoothen out the vertices. So let me draw a picture. So let us say you have a curve that looks like this, okay. So this is the vertex, let us say gamma of ak. The idea is to draw a little ball, look at a neighborhood disk around this point. So you have your tangent vectors here. So I am going to call this gamma of T1 and this is gamma of T2. So the idea is to actually connect the portion of the curve between these two by a smooth curve with the same initial with the same tangent vectors at gamma of T1. So you are basically smoothing out this curve, and one can choose this neighborhood small enough So choose neighborhood small enough so that the delta theta jump from gamma of T1, so let us say from this theta of T1 to theta of T2 is small enough so that the angle is between minus pi and pi. Okay, so then one can actually take a smooth curve, which is shown by blue in this picture, to interpolate between these 2 points, right, and then you just now we end up with a smooth curve without disturbing the total rotation angle. So now I just apply the first part for smooth curves and conclude that theta b minus theta a is still 2 pi. So this is of course a very hand wavy argument. So for a rigorous proof, refer to chapter 9 of John Lee's book on Riemannian manifolds. Okay. All right, so that basically completes the proof of the rotation angle theorem. So now we would like to generalize this to, so our next goal is to extend this to curved polygons on M. Okay. So let me recall the setup of local Gauss-Bonnet. Okay. So remember we were looking at these open subsets of M such that omega is completely contained inside a coordinate neighborhood and gamma is a parameterization of the boundary such that the boundary is a curved polygon which is positively oriented, positive in the sense of Stokes's theorem, right. So let xy be coordinates on U. So I can consider this omega to be sitting inside some open subset of R2 via these coordinates, except now the metric that I am using is an arbitrary metric G, right. So G I am looking at this surface M2 comma G, right. So we can think of U as a subset, as an open subset of R2 with a non-standard Riemannian metric given by G. So for instance in this Riemannian metric G, obviously del by del x and del by del y need not form an orthonormal frame, right, because otherwise of course your local patch would be flat, right. So instead we choose by Gram-Schmidt an orthonormal frame. So let E1 E2 be an orthonormal frame, orthonormal oriented frame. So oriented orthonormal frame with respect to this inner product G, with respect to our Riemannian metric G, such that I take E1 to be just a multiple of del by del x. So of course what is A in fact here? A is simply a factor that you multiply del by del x so that you get a vector of norm 1. So A will for instance just be the norm of del by del x inverse. the G norm inverse, right. So, I can always do that. I choose my E1 first and then use Gram-Schmidt process to construct E2, and I can do this so that I end up with an oriented basis. So, then sorry, I should have mentioned that that the speed of gamma is 1 wherever it is smooth. So, because the speed of gamma is 1, I can decompose the velocity vector as C1 of E1 of gamma t plus C2 E2 of gamma t, where C1 squared plus C2 squared is 1, okay. Or in other words, you can think of C1 C2 as points on a circle, okay. So, then using this basis E1 and E2, I again get a map given by the velocity vector. So, this is again a map from this interval a to b to S1, and I can again do this covering space trick. So, as before, we again get obtain a theta such that the following things hold. So, one, theta is smooth on the open intervals where gamma is smooth, okay. Then at the boundary points, at the non-smooth points, I again extend theta as before using the external angles. And then finally, it should satisfy this crucial relation that gamma dot of t is precisely cosine of theta t times E1 of gamma of t plus sine of theta of t times E2 of gamma of t, okay. So, this construction is exactly as before, but then a corollary to Hopf's theorem is the following. So, maybe I will write it as proposition. Since gamma is simple and closed, it is a curved polygon, if you take the total rotation angle of the tangent vector, that is still exactly 2 pi. Okay, and now the proof is simple, we have done all the hard work. So, we simply consider the following family. Of metrics parameterized by this parameter S, which is simply S times G plus 1 minus S times the Euclidean metric on the plane, okay. So, this is a family of metrics on this coordinate neighborhood U, okay. Now, for each GS, I choose a corresponding basis E1 of S and E2 of S as above, and each one will lead me to an angle theta S, and the key point is that theta S varies continuously in S, in this parameter S, right, where S is between 0 and 1, okay. But since gamma dot of B is equal to gamma dot of A, this implies that for any theta S of B minus theta S of A must be a multiple of 2 pi. Must be an integer multiple of 2 pi, right, because the tangent vector eventually comes back to the same velocity vector. So, it must have made at least a rotation that is a multiple of 2 pi, right. But then you have a so if you consider the function theta s of b minus theta s of a divided by 2 pi, this is an integer valued function and it is continuous in s. So, of course, it must be the constant function. So, this implies that theta b minus theta a, which is equal to theta 1, remember g1 is the metric g, right. So, because this is constant in s, this must be theta naught of b minus theta naught of a, but what is g naught? G naught is the Euclidean metric. For the Euclidean metric, we have already proved Hopf's rotation angle theorem and we know that the answer is 2 pi. Okay. So, this completes the proof on a general curved surface. So, now a corollary of this is simply that if you take the these differences, then and add on the sort of external angles, so I should be a bit careful. So let me just state the corollary. So, as a corollary we obtain the following, that if you take summation k going from 1 to m of ak minus 1 to ak theta dot plus all the external angles, then that is 2 pi. Okay, and the proof is now easy. By the fundamental theorem of calculus, what is this? This is theta of ak from so here you have your interval sort of ak minus 1 to ak. So, you take theta ak from the left minus theta ak minus 1 from the right. Okay, so now if you add up all of these, so if you sum over all k, then so let us start with k equals 1. So, you will have something like this a1 or let us start at maybe the right end point. So, you have theta of b minus theta of am minus 1 plus theta of am minus 1 minus theta of am minus 2 plus etc., until the last term is basically theta of a and theta of a1 minus. Okay. So, all of these alternate terms, notice that this thing is basically just going to be minus the external angle, right. So, if you add all of these up, you are basically going to get the end points minus the sum of all the external angles. Okay. So, if you take the external angles to the other side, you have proved the corollary. So, this is equal to this is equal to theta b minus theta a, which we know is equal to 2 pi. Okay. Alright, so now we have done all the hard work. So in the next lecture I am going to use this corollary to prove finally the local Gauss-Bonnet theorem. Alright, so that is it for this lecture. Thank you for your attention, and I will see you next time around. Thanks.